Hello students, today we will be discussing about the AC circuit. So we will be deriving the equation for the AC circuit containing the pure ohmic resistance. So first let us see what is an AC circuit. So AC circuit is nothing but the path in which the alternating current flows. Now you already know in a DC circuit the voltage and the current relationship is given by I is equal to V by R. Now you know that this relationship comes from the formula V is equal to I into R. But what about the AC circuit? Now you know in an AC circuit what happens. So if you just see the waveform of the alternating quantity. So say a voltage or the current. Now what happens in the AC circuit? If you see the waveform of the alternating quantity, you can see that the voltage and the current will change from time to time. Voltage and current will keep on changing from time to time, and so it will give rise to the magnetic and electrostatic effects. So when we are speaking about the AC circuit, we also have to consider about the inductance and the capacitance along with the resistance. So here we will be discussing the circuits for different type of circuits. So first we will discuss the AC circuit containing pure ohmic resistance, AC circuit containing pure capacitance, so pure capacitive circuit, then followed by the AC circuit containing the pure inductance, so let us go through the AC circuit containing pure ohmic resistance. So let me first draw the circuit. So I am going to consider the resistor where an alternating voltage is applied. So the alternating voltage that I am going to apply is V is equal to Vm sine omega t. This is the resistor R. So the voltage across the resistor R is given by VR. Now, current I flows in the circuit. So you can see here alternating voltage V is equal to Vm sine omega t is applied to the circuit. So when you are going to apply the alternating voltage V equal to Vm sine omega t across this resistance, what happens is electrons will flow in one direction during the first half cycle, whereas in the next half cycle it will flow in the opposite direction. Now because of this alternating voltage, the alternating current will also flow in the circuit. So now the drop across the resistance, let me take this as equation 1. So drop across the resistance is given by V is equal to I into R. Now if you substitute the value of V in the equation 1, what will happen? You will get Vm sine omega t equal to I into R. So from this equation, you can see the instantaneous value of current I is equal to Vm by R into sine omega t. So let me take this as equation 2. So I is equal to Vm by R into sine omega t. Now from this equation you can see here, if the component sine omega t is equal to 1, then that means the current will be maximum, right? Now when will be sine omega t equal to 1? That is when sine 90 degree is equal to 1, right? So that means current will be maximum when sine omega t equal to 1. I can write that maximum current as Im. So I can also specify current Im is equal to Vm by R. So maximum current Im is equal to Vm by R. Now substitute this equation, let us substitute this maximum current in the equation 2. So what will you get? I is equal to Im sine omega t. So this is the expression for the instantaneous value of the current for a pure ohmic resistance. So this is very, very important. Now, we had considered at the beginning that the applied voltage is V equal to Vm sine omega t, and at the end we have ended up with the equation of the current, which is equal to I equal to Im sine omega t. Now looking at the equations, we can clearly say that both the voltage and the current are in phase. Therefore, if I want to draw the waveform for the voltage and current, how will it look? So let me draw the waveform for the voltage and current for a pure ohmic resistance. So let me draw the current waveform first. So current is equal to I equal to Im sine omega t, which means current starts from the origin or at the 0 point. So if this is the current waveform, then let me draw the voltage waveform. So this is the voltage, V is equal to Vm sine omega t, whereas this is the current waveform, I equal to Im sine omega t. So you can see both are in phase with each other. So therefore this is the current and this is the voltage and this is omega t. So next, let us find out what is the power equation. Now, voltage and current are changing at every instant, right? So the instantaneous power in the circuit is nothing but, power is obtained by the product of the voltage and the current. So by using that, let me find out what is the instantaneous power. So instantaneous power is equal to V into I. So V is nothing but Vm sine omega t into current Im sine omega t. Now Vm and Im are constants. Vm into Im. Sine omega t into sine omega t can be written as sine square omega t. Now Vm into Im into sine square omega t can also be written as 1 minus cos 2 omega t by 2. That means now we have got two equations. One is Vm into Im by 2 minus Vm Im into cos 2 omega t by 2. So now you have got two components. One is you have got a constant component, that is Vm into Im by 2. Now another component is this component, which is the fluctuating component. Now you can see this fluctuating component, it has got a double frequency, right? You can see cos 2 omega t. That means it has the frequency which is double that of the voltage and the current wave, right? So therefore the average value of this component is nothing but 0. So average value of this fluctuating component over the complete cycle is nothing but 0. Therefore, I am going to only consider one of the component, that is Vm into Im by 2. So therefore, P is equal to Vm into Im by 2. Now, I can write this component also as Vm by root 2 into Im by root 2, right? You know that 2 also can be written as root 2 into root 2. So therefore, I have written it like this. Okay. So what is Vm by root 2? Vm by root 2 is nothing but Vrms. Im by root 2 is nothing but Irms, right? Therefore, I can also write it as P is equal to V into I or Vrms into Irms value. So this is the power equation for pure ohmic resistance. Next, let us find out what is the power curve. Let me first draw the power curve for the pure ohmic resistance. Now first, let you know that V is equal to Vm sin omega t and current is equal to I equal to Im sin omega t, right? So this is current I equal to Im sin omega t. If we draw another curve, this is V equal to Vm sin omega t. So V I. Now I need to draw the power curve. Now what is power for the pure ohmic resistance? It is V is equal to V into I, right? Or you can say instantaneous power. How did we find out? P is equal to Vm sin omega t into Im sin omega t. This is how we had found out the equation for pure instantaneous power. Vm into Im into sin square omega t, right? So this was our power. So you know now the power we are going to find out. It is nothing but the product of the voltage and current. That means now if you take the first half of the cycle, you can say it is your power curve will be nothing but. Now again here in the next half cycle. Now although your current and voltage both are negative, now negative into negative will be positive. That means the power curve here also in the next half cycle will also be positive. So what is this power curve? It is nothing but P is equal to Vm into Im into sin square omega t. This is omega t. So P. Okay. So this is how your power curve will look. Now if you analyze this waveform properly, then you can say for a pure ohmic resistance, the power is not zero at all the time. You can see that only at some points or only at some instances the power is 0. So here you can see at point 0 and at point A, at point B, you can see the power is becoming 0, right? And rest at all the times the power is positive, but it is never negative. So this is about your AC circuit containing pure ohmic resistance, where the power will never be negative. It will always be positive, and at some instances it will become 0.